Okay, again, I'm going to draw our bolt or our fastener. Okay. Then I'm going to draw our plate. So these are our plates, right? So if you look at double shear configuration over here, hold on, I'm going to get rid of this. Okay. And then this is member number 1, member number 2, and member number 3. So we call this member number 1, member number 2, and this is member number 3, right? And over here then, right? So we know that we have a applied force over here. So this is our P, and over here is P over 2. Okay, we are assuming member number 1 and number 3 take half the load. So failure now will occur here, right? We know that failure now will occur here, where I circling. I do. So these are your idealized failure region. So the formula changed slightly now. Okay, so for double shear, right? Shear stress is equal to P divided by twice the area. Okay, so why twice the area? Because the failure region, there's one failure region at the top, there's one failure region at the where? At the bottom. Okay, so now we come back to our problem. So now all of you know what is a single shear, double shear. Okay, so now coming back to our problem, the problem states that our structure is under a single shear configuration, or the fastener resistance force is a single shear. So when they test the fastener resistance force, they test it under this configuration only. Okay, they test it under that configuration. But under double shear configuration, okay, so this is double shear configuration, you have to have P. Now you have what? Twice the area. Okay, you're going to have twice the area. So now, how does this work now? Okay, so this is single shear. So double shear means now failure, right, will occur in either this region, or before we go on, what we see over here, right? What we see over here in our problem, is it a single shear problem or double shear problem? So if we look at here, you have member number 1, you have member number 2, and then you have member number 3. So altogether, you have 3 members laying down on one bolt. You got a single continuous bolt over here. Okay, so if you were to look which one it is, so if it's a single shear, you only have what? 2 members. Double shear, you have 1, 2, and you have what? 3 members. So for this case, this is a what? It's applied in a double shear configuration. Okay, not single shear, but double shear. Okay, but the test to test or the experiment to test the resistance force is only done in what? In single shear. Okay, so what must be done over here. So I'll tell you what must be done. So let's look at mode 1 failure first, which is failure at the joints. What is given is the fastener resistance is 600 pounds, and the spacing is what? The spacing is 6 inches. Okay, let's look at that first. Okay, right. Before we go on, what we are trying to determine, which unfortunately I miss it, is we are trying to determine the maximum load P. So we want to determine what is our P. Okay, right. So now I'm going to copy this. I'm going to go to. So we are still going to start with the problem. I'm still going to carry on with mode 1 failure. Which is failure due to the fastener. Okay, so we know that Q is equal to resistance. Did I call resistance force? I could not remember what I call it. Fastener resistance force divided by spacing. Okay, so this will be equal. We know that this is 600 divided by spacing is 6. Okay, and then we need to multiply a 2 over here, because now we have what? Double shear configuration. Okay, because to fail this pin, okay, to fail this structure over here, you have to fail one side and you have to fail the other side. So it's under a double shear configuration. Okay, so this will be equal to 600 times 2 divided by 6 is equal to 200. Okay, 600 is equal to 200 pound per inch of force. Okay, right. So once we have done this, right, we want to determine P. So I'm not going to waste your time to calculate I. I'm just going to write I. Okay, given that I, the second moment of area, so this is IZZ, is equal to 2902 inch to power 4. As I said, I'm not going to calculate this all over again. And then the centroid can be done by observation. We know that the centroid is here. Okay, we know the centroid is exactly at the center. Okay, so the next thing we ask us, hey, then what is the first moment of area, right? Because we already know what is Q. Next, we're going to relate Q is equal to PQ over IZZ, right? And we know our IZZ. Next is our Q. We will do V later on, okay? So for this to fail, if we have the Vy over here or the V over here, remember what I said. The member must distribute the load first. Okay, so the member must distribute all the Q first. Okay, so all the load you will distribute first. After it distribute, then it will transmit. Okay, so the first moment of area to take is this entire area that I'm highlighting it in green. Okay, that I'm highlighting in green. So is this entire area? Okay, is this entire area that I'm highlighting in green? You don't need to take. You only need to analyze either the top or the bottom, because the first moment of area cannot cross the what? Cannot cross the centroid. Okay, so we just analyze the top. Okay, so from here we are going to determine our QZ. Okay, our QZ now. So width, depth, Y bar. So the width we can see 6 inches. The depth is 4 inch, because you have to distribute in the entire member first. Then you can transmit. If you don't have this theory in mind, you will say, why don't it stop at the what? At the fastener? No, you have to distribute in the entire member first. Okay, so that's why I multiply by 4, and then the Y bar is equal to 5 plus 2. Okay, so this will be equal to 7 times 6 times 4. So this will be equal to 168 inch cube. Okay, so now we have our Q. So what is our V? Okay, so we are going to determine our V max. Okay, we are going to determine our V max. So we are going to carry out, we're going to draw our free body diagram first. Okay, so we draw our free body diagram. So this is our member. Okay, so this is our point A, and this is our point B. And what is applied on the center? This is our P. Okay, so we are also given that from here to here is equal to 4 multiplied by 12, which is equal to 48 inches. We have to convert everything in inches because our what? Our stresses are in pounds per square inch, so everything has to be in inches. Okay, so likewise from here to here is also 48 inch. So now we are going to apply static analysis. Okay, and we know we have a AY over here, and we know that we have a BY over here. Okay, we're going to put, so due to symmetrical loading and geometry, we're going to declare that AY is equal to BY. Okay, so you just do summation of forces in the Y direction is equal to 0. So AY plus by BY minus P is equal to 0. Okay, because AY is equal to BY, we have 2AY is equal to P. AY, okay, AY will be equal to P over 2, and this is equal to BY also. Okay, so when we draw our shear force diagram, okay, it'll be so straightforward. So we know that this is our vertical axis, this is our V, and then we have our horizontal axis. And this is our 0. This is our x. So over here is P over 2. And down here is minus P over 2. And this is where the force is applied. It's at the center. So the shear force looks like this, or the shear force distribution looks like this. So you have a horizontal line coming over. Then you have a vertical line coming down. So P over 2 at point A for a long while. And then you have P, magnitude of P coming down. Okay. And then finally, you have minus P over 2 from here to here. Okay. I should have drawn this longer. Okay. X. And then from here, it goes back to our 0 by, so it goes back by P over 2.